Started. Want to talk to you for a little bit today about mode shapes and natural frequencies. Okay, so this is going to be for assignment 8. I have assignment 8 here for you. It's also posted online. I'll go ahead and give you a copy of this so you can see what this looks like. The printer is, something's wrong with it. It's really, really light. But I think if you squint at it, you can read it. Okay, so we are going to be looking at the next couple of lectures about different capabilities of SolidWorks to do types of analysis in addition to just the static analysis that we've been working on. Okay, so to date, we've looked at a bunch of different element types, but all of the analyses that we've done have been a static analysis. So the basic process is create the geometry, apply some constraints, apply some forces. Those forces are just static loads. And then find out how much those forces cause the structure to deflect and what kind of stresses are the result of that. Okay, so that's everything that we've done so far has been that type of analysis. There's many other types of analysis that we could do, and so I want to spend a little bit of time on 3 different types so that you have a little more well-rounded view of some of the capabilities of SolidWorks. So the ones today are on mode shapes and natural frequencies. Then we're going to talk a little bit about nonlinear analyses and buckling next time, and then the last one we'll do a little bit of thermal analysis, because for some of you that might be useful in future endeavors, being able to do a little bit of thermal analysis for a heat sink or something related to heat dissipation in a piece of equipment. For example, I just told you I've been working on moving, and I had to move the cable modem to the new place and had it hooked up, and I was amazed at the amount of heat that's being generated off of that cable modem. And I guess I just never touched it when it was plugged in and operating. But thermal management of devices is obviously a significant portion of the design sometimes. So we'll be looking at those types of analysis. So I want to talk a little bit about the theory of what we're doing, and then we'll talk briefly about how SolidWorks approaches that. But I thought it might be useful for us to look at the assignment first, so you kind of get an idea of what we're going to be doing with this. So the first one here, you look at that. What does that look like? It's the same truss we've been looking at a couple times, right?
Yeah.
Okay, so my intention here is not to make you spend lots and lots of time generating geometry. We're assuming that you have sufficient capabilities in SolidWorks that you can create the geometry. So we're reusing structures that we've already created, so you can open those files and do a new type of analysis on it, and then you don't have to regenerate all the geometry. Okay, so we've seen this truss before. This time it says determine the first 5 non-zero natural frequencies and mode shapes for the following cases. And then it says restrict the truss to in-plane displacements only. So we want to keep the constraints on here. If you remember back when we were doing the trusses, we put some constraints on these so that they stayed in the XY plane and didn't deflect in the Z direction. Okay, so keep those constraints on those truss. And we're going to find out what its natural frequencies are and what its mode shapes are. Okay? And we'll obviously talk about what those are if you don't remember from dynamics or someplace what that means. Okay? On the back side, there is 2 more problems. One is 2 channel sections welded together. So it's 2 C channels that have a bend in them. And we're going to do the same thing the first 5 non-zero natural frequencies. Okay? And then the third one there is a cylindrical shell, so it's curved and it's tapered. And this one, you might have to get a little creative with your SolidWorks skills as far as making that shape. There's a couple different alternatives to doing that. You need to create a curved shell that is tapered in length. So making a curved shell that is constant width is easy. And there's a couple of different ways of doing this with in SolidWorks. Okay? So one of the things you notice in all these, they say the first 5 non-zero natural frequencies. So, what does that imply?
There's more than 5.
Okay, there's more than 5. I'm asking obvious questions, so don't be afraid to give me an obvious answer. Okay, so there's more than 5. What else does that statement indicate? This is a question in logic. The first 5 non-zero natural frequencies.
It's going to be a number.
Huh?
It's not going to be 0.
Okay. If I'm wanting the first 5 non-zero natural frequency, that means there's going to be some that are 0, right? Okay? So, one of the things that's a little bit different, I'm maybe jumping into talking about doing the analysis a little bit here early, but since I brought it up, go ahead and talk about it, is depending on how your model is constrained, you're going to get 0 you're going to get frequencies that are 0. And we don't care about that because a natural frequency that is 0 means rigid body motion. Okay? So depending on how you have your structure constrained, if you have an unconstrained model, you will have rigid body motion, which means you'll have some natural frequencies that have a frequency of 0. So for problem number 2 here, it says the structure is unsupported. If you think back to our previous statics analysis, you couldn't do an analysis on a structure that doesn't have any supports, right? That was kind of part of the thing. In order to make our stiffness matrix determinate, we had to apply boundary conditions, which meant that it had to have some type of supports. So something that's a little different here with our natural frequencies and mode shapes is that we can have models that are theoretically floating in space. So that's what this means on the second problem where it says it's unsupported. You don't have to put any constraints on this model. But because we don't, the first several natural frequencies are going to be rigid body motion. So can you predict how many 0 natural frequencies we're going to have? Zero natural frequencies are going to be related to constraints. If I have no constraints, that means it's going to have rigid body motion. If I have rigid body motions, how many different ways can I have a structure move in 3-dimensional space? Okay, let's count them. If I call that the x direction, I can move in one direction, right? That's 1. This is the y direction. That's 2. So continuing on that process, how many different ways can it move? 6, right? Okay? So it can move x direction, it can move in the y direction, it can move in the z direction. That's 3. And then we also have the rotational. It can spin about the x-axis, it can spin about the y-axis, and it can spin about the z-axis. Okay, so if for problem number 2, we're going to have 6 degrees of freedom that are unconstrained, so we're going to have 6 natural frequency modes that have a frequency of 0. And we don't care about those because that's rigid body motion. Okay, that's why I'm going through this whole explanation, is so you understand a little bit. Because when you do problem number 2, if you say, give me the first 5 natural frequencies, it will give you the first 5, which will be all 0, and will all be related to rigid body motion. So in SolidWorks, what do I need to ask for? Modes number 7 through 12, right? Or I guess actually 7, 8, 9, 10, 11. For the first 5. Okay? So in our analysis, we need to tell SolidWorks to calculate the first 11 so that we have 5 non-zero ones. Now obviously, as you do the analysis, if you just ask for the first 5, it will tell you all zeros, and you look at the results and say, well, they're all 0, so now give me the next 5. And then if you have a few zeros in there, then you can keep increasing your increment too. But if we think about this a little bit, if you just tell me modes 0 through, or 1 through 11, then we'll get 5 non-zero ones that we'll report. Okay? Now, other models that might be fully constrained, your first non-zero natural frequency might be the very first mode. If you don't have any rigid body, then your first frequency that has a non-zero value will be your first one. So then you just need to ask for modes 1 through 5. Okay? All right. So those are the things I can think of with the models here. I guess maybe one more thing to say about these. So the first one, the truss one, you can just use the beams that we used previously. So your finite element model can be beams. For 2 and 3, you need to model those as shells at a minimum, or possibly, I mean, you could do it as solids if you really feel the need to do some solid work. But shells would be good for both 2 and 3. Okay? In order to capture the modes, we have to capture the cross-section accurately. And for 2 and 3, modeling those as beams or something like that is oversimplifying it too much. We need to use at least 2-dimensional elements like shells for those problems. Okay, let's talk a little bit about natural frequencies and mode shapes. Have you guys had a little bit on this already?
A little bit.
Possibly in dynamics or physics or someplace. Can you tell me anything? Do you remember anything about natural frequencies or mode shapes? Pulling teeth this morning. Or you need to eat your Wheaties or something so that we're more. Okay, so you know nothing about natural frequencies and mode shapes. That's basically what I'm hearing. Okay, it's all right. So when we're talking about natural frequencies and mode shapes, we're interested in the way a structure vibrates. And the reason we're interested in it is because there are vibrations that can be really detrimental to the structure itself. Some examples of that, I was reading an article yesterday about some companies that are coming up with innovative ways of making elevators for very large buildings. So right now, and I'll quote some numbers, but I could be erroneous because I wasn't thinking about this until this moment, so I didn't double check my facts. But if I remember in the article correctly, it was saying that conventional elevators are limited to about 1,600 feet of building height. Pretty sure that's what I remember. So with a conventional elevator with steel cabling lifting the elevator, our current limits are about 1,600 feet, which means that we've got buildings that are taller than that And thus, you can't ride the same elevator from the ground floor to the very top. And so what that means is they have to have some lobby halfway up that people get off the elevator, switch elevators, and then continue on going up, which obviously is inefficient and annoying and so forth. So people are trying to get around that. There's several different technologies, but what is it that limits the conventional elevator to 1,600 feet? Well, one of it is just the weight of the cable. It gets so long and so big that it becomes impractical to make the cables that long. Interestingly, the other thing that becomes a problem is the natural frequency of the cable that's hanging there. And the article was saying that when the wind is blowing and the building is swaying, the elevator cables match the frequency of the building sway. And when that happens, then the cables start whipping back and forth in the elevator shaft, and it actually can oscillate enough that they start hitting the walls. And clearly that's not a desirable characteristic. And so we have to limit the length of the cable to not match a natural frequency of the building, which will cause them to whip. So if you have a structure that has a particular natural frequency and you vibrate it at that natural frequency, we'll look at it in a little more detail in a second, you will theoretically get infinite displacements if there's no damping. Okay? So vibrating at a natural frequency is a very bad thing if you don't want that vibration to occur. A really good example of that you may have experienced is if you have a car wheel that is out of balance. Okay? And actually, a couple years ago, I was leaving here and I got on 265 and I was following this car that was shaking badly. And I was looking at it, and I wish I had video of this because I'm going to say this and you're not going to believe me. But I was looking at it, and the right rear tire of that car was so badly out of balance it was lifting off the ground. Okay, I could see air underneath the wheel, an inch or two, and I was like, oh my God, it's like, pull over. Okay, so really bad situation. And of course, the poor person in the car is getting shook all over the place. Now, the thing that person obviously didn't realize, and I wasn't going to try to yell at them at 65 miles an hour, but is they were driving at the natural frequency of that unbalanced tire. To stop it from vibrating so badly, if they slowed down or sped up, it would no longer be at its natural frequency, and it would still vibrate, but it wouldn't be the ridiculous bouncing off the ground kind of vibrations. Okay? And you may have noticed this before, and if you have a vehicle that has a tire out of balance, that if you drive 37 miles an hour, the thing shakes like it's going to fall apart. But if you speed up or you slow down, it stops. Okay? So, what that's called is resonance. So when something is resonating, it is vibrating at its natural frequency, and if there's no damping in the system, then it will, the vibrations will theoretically go to infinity, which of course means it explodes and shakes itself apart. Now, the reality of most every physical system has some type of damping in it, and as a result, they don't go to infinity, but they go to very, very high values. Okay? Another example of my Jeep Cherokee that I had from 96 to 2008 or so. I didn't realize it at the time, but there's a damper in the front end for the steering. And the damper or the shock absorber had failed. And I would notice that occasionally I'd hit a bump and all of a sudden the whole thing would start shaking like nuts. And it would continue to shake unless I stopped or slowed down significantly. And then once I slowed down significantly and it stopped, then I could keep going again. So once again, it was a resonance problem, a vibrations problem. Without the dampening of that shock absorber, then it would cause the front two wheels to start oscillating, start resonating, and unless I changed the frequency of the vehicle, it would continue to vibrate like that. Okay, so there's some real world examples of why we don't want this to happen. When I was working in industry, we were building machines that vibrated. So great big industrial machines that shook, And we had to be very, very careful about natural frequencies, because if you put this machine on a structure that has a resonant frequency at the operating speed of the machine, it will shake the whole building. Occasionally we get calls from customers, and you know, one particular example, there was a foundry, and unfortunately in some places there's industrial foundry-like places with people living right next door. And they installed some new equipment, they turned it on, and they started getting calls. The neighbors were complaining that stuff on their shelves were shaking off of the wall. And what had happened was, through the groundwater and the characteristics of the soil in the area, the vibrations in the plant were being transmitted to people's houses, and it was causing vibrations to occur in their house. Another really common thing is we put equipment in a building on the second floor or third floor, and civil engineers typically don't check natural frequencies of buildings for vibrations from industrial equipment. That's not something that generally comes into the code. You know, they check stuff like earthquakes and wind loads and snow loads and all those kinds of things, but they typically don't worry about vibrations. And so it's really common in buildings to have some frequencies that might be low enough that when you put a piece of equipment in the machine, it starts shaking building structure. You know, and so you look at these giant beams, and they're shaking pretty badly because they're at a resonant frequency. Okay, so it can be a real problem, and if it's not treated, then obviously it makes the structure unusable. You know, people can't stand on a floor that's shaken up and down by a ½ an inch kind of thing. Or even if the magnitude is significantly less than that, the feeling, the vibrations are detrimental to productive work kind of thing. Or if, you know, your monitor won't stay on your desk because it keeps vibrating off the back, you know, that's a problem. So, small forces, small input forces result in really large displacements. That's the characteristic of a natural frequency problem. And they happen at particular frequencies for the structure. And the thing is, we can calculate those, and if we can calculate those, then we can design our structures such that it's not resonant at a frequency that we know it's going to be driven at. So let's say that you're going to put a motor on a structure, and you know that motor is going to run at 1800 RPM, then you need to make sure that you don't have a natural frequency at 1800 RPM. Because if you do, it will shake itself apart. Okay? Related to that, I talked about the place I used to work. We kind of took advantage of this as well. We made conveyors that were hundreds of feet long that were powered by like a 5 horsepower motor. You know, little bitty motor on a conveyor that's, you know, hundreds of feet long. And we were able to do that because we were taking advantage of the spring systems that were operating at their natural frequency. So a little motor putting in a little force was able to shake a giant long conveyor because it was operating at its natural frequency. So we can use this for good things too. I don't want to imply that natural frequencies are always bad. If you want something to vibrate at a particular frequency with a low input power, then you design it so that you shake it at its natural frequency, and it will shake at that frequency for you. So if you work in a manufacturing plant, you've seen vibratory conveyors or bowl feeders. Those might be brute force driven, which means that it's just a weight that pounds on it. But it might also be sitting on springs that drive it at a natural frequency. Okay? All right, so we're not going to go through all of the math, but if you want to derive some of this equations, we're talking about spring mass damper systems. So you probably looked at these in physics. We have a mass, it's connected to a spring that's connected to the wall. We have some kind of force input into it, and it's going to displace in some way due to that force. Okay, that's a basic spring system. If we put a damper on it, then that will attenuate the displacements. So what do the shock absorbers in your car do? Why do we have shock absorbers?
Shock.
Okay.
Dampening.
Not really. So when you hit a pothole, what does the shock absorber do? Dampens. Doesn't absorb the shock. What absorbs the shock?
Spring.
The spring, right? When you hit the pothole, the spring lets the wheel bounce down and absorbs the shock. So why do we put shock absorbers on it? It dampens the bounce after the hole, right? If you don't have shock absorbers, can you drive a car without shock absorbers? Sure.
Wouldn't be much fun.
What's going to happen? You're just going to bounce down the road, right? Because you're not dampening the shocks that are being input into it. So shock absorbers on a car are dampers that it takes the hit, but then it dampens out the response. And I think I got a plot. Yeah, there we go. Okay, so spring mass system. If we input a force, it's going to respond to that force. And if the force continues on, it's going to keep oscillating forever. We put a damper on there, and the initial response might be large, but then it bounces out. If your shocks are properly absorbed or properly working and installed on your vehicle, if you take and you push down on the bumper, it should go down and come back up and pretty much stop. Okay, you take the shock absorbers off, you push it down, and it's going to sit there and bounce for a second. Now, it doesn't bounce forever because the car itself has some natural damping characteristics. But the shock absorbers are there to pretty much cut that oscillation out as quickly as possible. The whole point of that being that you get a nicer, smoother ride that's more comfortable, right? Okay? All right. So for a single degree of freedom, we have a single mass with a single spring. Then the natural frequency is the square root of the stiffness of the system divided by the mass of the system. So for the conveyors that I used to work on, we would figure out the total K rate of all the springs in the system, divide that by the mass of the vibrating part of the machine, take the square root of that, and that gives us the natural frequency. And so we have a 300-foot long conveyor, and we would adjust the numbers of springs in it such that the natural frequency of that thing was like 300 RPM. And then we spin the motor at 300 RPM, and we get a nice regular vibration of that conveyor that allows us to convey large quantities of materials with very, very little power input. Okay? So that's natural frequencies. That's a little bit of background on natural frequencies. Why do we care? Sometimes we want to avoid them. In rare instances, we actually want to tune to them. And then the other side of this is mode shapes. And mode shapes is the shape that the structure displaces into at the various natural frequencies. So for every natural frequency, there will be a mode shape that is associated with that. So if we have a cantilever beam, so this top example is a cantilever beam, and our displacement possibilities is perpendicular, like a cantilever beam is. We calculate the first natural frequency. The first mode shape is going to look like this, with it just whipping up. And then, of course, this also goes in the negative direction, so bending up and then bending down. And you've seen that before. If you take a stick and you shake it, you see the end of it whipping back and forth, right? That's the first mode shape. So whatever the lowest natural frequency is, the deformation at that frequency will be that whipping back and forth. When we go to higher frequencies, that displacement gets more complicated. So taking that same idea in the second mode, this middle part actually bends down and the top of it bends up. And then this reverses and bends this way. That would be the second mode. Okay? This gets into waves and things like that you might have seen before. So going with the automotive analogies, have you ever looked at depending on what kind of vehicle you have, your radio antenna as you're driving, and it's whipping sometimes? It will whip at particular natural frequencies, and one of the things that you might notice, if you look really, really carefully, so here's my antenna on the car, it might be whipping back and forth like that. Okay, so that's just a higher natural frequency than first or second mode. And so when you look at it, it actually looks like, you know, usually it's happening so quickly, it kind of looks like that. And there are modes, there are points along that length where the displacement is 0, and then there are places where it is very high. Or if you go to the Science Museum, a lot of times they'll have like tension strings or like a guitar string. Or guitar string. You know, the first mode would be like this, vibrating like this. Second mode, at a higher frequency, would be like this. Third mode, like that, and so forth. Okay, so what is the act of tuning guitar string? Okay, you're changing the tension in the wire, and you're changing the frequencies that it vibrates at, right? And thus we get different sounds based on how tight that string is, the way it vibrates. Okay, does that make sense? So on our finite element analysis, when we plot the mode shapes, it's going to show you the different ways that the structure is going to deflect at the particular frequencies that we're interested at. Okay, you always, the first mode will always be the simplest, and then at the higher frequencies you'll get crazier and crazier looking displacement shapes. All right, we talked earlier about dampening and how that affects the displacements. So this would be a chart showing different levels of dampening. It doesn't show 0 dampening. 0 would be an infinite. So when we hit natural frequency, we get a huge peak. When we're lower than natural frequency or above natural frequency, we have reduced amounts of response. So if my input is this, is 1, when I'm at really low frequency, if I'm inputting 1, I get displacement of 1. If you think about that, if I have a mass hanging from a spring, if I move it really slowly, the spring doesn't really stretch and it just moves up and down, right? So my input is equal to 1, my output, my movement of the mass would be 1. So at very low speeds, it's 1 to 1. As I approach the natural frequency, I will get extremely large displacements. And then once I pass the natural frequency, then that'll get smaller and smaller. That's what this chart is showing us. Okay, so again, reinforcing the idea with little dampening, we do not want to be operating at a natural frequency because we'll get extremely large displacements. Okay, so that's the theory. Talking about SolidWorks, the process for doing an analysis. You want to create the geometry like we have been. So create the geometry like always. Start the analysis package. And when you say new study, instead of choosing static, you want to choose the modal analysis. Okay? And I forgot to look. I didn't look to make sure that SolidWorks says modal analysis, or maybe it says frequency analysis. I forget now exactly. Is it frequency analysis? Okay. Different software uses different terms. So do frequency analysis. And the interesting thing here is that if the problem has constraints, then you need to apply the constraints. Okay, just like we have previously. But if, like problem number 2, it says it's unconstrained, you can just skip the process of applying constraints. We still have to apply a material like we always have. If there are forces in the problem, then put the forces on the model. But I think you'll discover that the forces are not going to have an effect on the mode shapes. Okay, this is a characteristic of the stiffness and the mass of the structure. It's not a characteristic of forces that are being applied to it. And then you can do the solution. And when in the options for the solution, it will ask you how many natural frequencies do you want. The default, I believe, is 5. So if we're doing problem number 2 and you say, and you just run with the defaults, you're going to get 5 natural frequencies that are all 0. So you got to go back and change that default to give you more so that you have the non-zero ones. Okay? Once you've run the analysis, then you can view the outputs just like we have been. You can create the displacement plots, and you can specify which frequency does it base the displacements on. And so obviously for your assignments, you will have to, so talking about the assignments a little bit, this is going to be a little bit different than what I've told you so far. Okay, so I told you give me one characteristic plot of the displacement. Well, now we need all of them, right? Okay, I'm not interested in stresses for this problem. You don't need to do any stress plots, but you need to do a displacement plot for each frequency so that we can see what the different mode shapes look like. You should probably put the all the modes in a table as far as their frequencies to summarize them. What kind of hand calculations can you do with this? That's a trick question. Okay, there's not really much of a hand calculation you can do for these. So, what I'm going to ask you to do is put some kind of statement of, does this make any sense? Okay, look at be critical of your results. Think about it when you do your analysis. If I know I have no constraints, but I get a value for my very first mode of frequency, then that should be an alarm that we've got a problem. Okay. Look at the displaced shapes. Do they make sense? Does that seem like a logical way that it can vibrate? Now, some of this is going to come from experience. So the first couple times you look at these, they might all look crazy to you. But you should start to see that they have some characteristics, some similarities to each other. So on your reports, there's not going to be much of anything that you can do hand calculation-wise. So I'm going to want you to compare your results to each other. So for example, in the first one it says, model the truss using fixed rigid joints, and then model it again with pin joints and compare the differences. What do you expect is going to happen for the pin jointed truss? The frequencies for that one, are they going to be higher or lower than for the rigid?
Probably lower.
Probably lower, right? So there's less stiffness. It's more flexible. That's going to tend to bring the natural frequencies down. So you can compare your pin joints to your rigid joints, and we should probably get lower frequencies for the pin connected one. So we can do those kinds of like sanity checks of, does this make logical sense for my results? Okay? Questions about any of that? Okay. That's assignment 8 then. Okay.